Prestressed Concrete from the S8A AC Engineering PRP training program. So thank you, Bodhi, for introducing me. A little bit more on myself. Actually, I'm from Bangladesh originally. My home district is Faridpur. Then I grew up in the city of Dhaka, and then I went to St. Gregory's High School and Notre Dame College. Then went to BUET, civil engineering, and I was a faculty member in BUET for a few years. Then I have been overseas for a long time. As Bodhi mentioned, I'm currently at the University of Texas at Arlington. Before that, I was in Florida for many years. But my roots are still in Bangladesh, and I still frequently go back. And I have a lot of ties, family ties, and also professional ties. And this is just one of those few projects that I'm involved with Bangladesh, trying to improve the professional knowledge in Bangladesh and improve the resiliency of Bangladesh infrastructure. So today, we'll be talking about prestressed concrete design. Granted that some of you may have a lot of knowledge on prestressed concrete and you may be using almost every day in design and construction, or some of you may be a little bit not so familiar with prestressed concrete. So I'll be taking a little bit slow in the beginning, trying to describe the essence of prestressed concrete and why is it exotic material. Of course, we know that concrete itself, reinforced concrete, is exotic material. It has a lot of flexibility and a lot of other virtues, but prestressed concrete takes it one major step forward. So I'll discuss that, how prestressed concrete is so prevalent these days in world infrastructure in concrete. So my lecture today will be geared more general towards concrete design, not specifically to buildings or bridges. As you know, this curriculum will be having eventually sessions on bridge design, which I'll be covering. I have 5 sessions on bridge design, which will be happening in late February and early March. I hope you'll join them because this course here is sort of prelude to concrete bridge design. There is very little opportunity to design modern concrete bridges without prestressed concrete. So I will talk about that a little bit. So hopefully you'll be joining those sessions as well and try to remember what we learned today. And as you know, there will be question and answer session at the end. Feel free to post your questions there, and we'll be trying to answer as many as we can today. So today, and right now it's about 8:10 a.m. in Texas time. So about 11 a.m. I have a class here. I'm teaching undergraduate reinforced concrete with our 60 students. Students are not coming to class right now. We're doing online teaching right now because of the Omicron surge in USA. Hopefully, we are told that we go back to classroom next month. So because of that, I have to leave a little bit early. So by 10:45 p.m. your time, I'll hopefully say Khuda Hafiz or goodbye. And hopefully by then, we'll be covering all the major parts of this lecture. So let's start with the very basic stuff here, reinforced concrete, as Dr. Ghosh may have been speaking about that in the last few sessions. We know about reinforced concrete. What's reinforced concrete? Well, this is a regular reinforced concrete beam. Typically, we show simple supports, but in practice, we rarely have a simple supports, as you know. So in my class, I have been teaching reinforced concrete, and I have been talking about simple supports. So there's roller and hinge. And one student asked me, "Sir, I went to practice and I'm talking about simple support, and I couldn't find a roller or hinge in practice." I said, "Listen, that's idealization. We really don't have a roller or hinge in practice. We simulate that. For example, in the bridge, we can have elastomeric bearing pad that simulates roller support. But anyway, for an idealization case, this is okay. So here's a simply supported beam with 2 point loads. And here's a typical cross-section of reinforced concrete. As we know that these are typically steel rebars. There are 2 layers here. And the main reason of providing steel rebar is to negate the weak tensile capacity of concrete here. Under positive bending moment, as you can appreciate, there will be tension in the bottom of the beam. and compression on top of the beam. So concrete is reasonably strong in compression, but quite a bit weak in tension. And that's typical of a brittle material. It can be concrete, it can be glass, it can be rock, or any other brittle material. So otherwise, concrete is a very good material. It has a lot of other virtues. It has fire resistance. It has reasonably good compression and strength. It can be molded in different shapes. It's flexible, but that weakness is negated by these rebars we place in there. So under regular reinforced concrete, these reinforcements are passive when they're placed in the concrete. So typically they are placed before the concrete is cast. And at the time, the steel has no stress. Then we cast the concrete around it, as you know, and then we apply all kinds of load, dead load, live load, wind load, earthquake load, or whatever. Under that, the steel goes into tension, and that allows the steel to contribute to the tensile capacity of the beam. As a result, the beam has increased capacity and reduced deflection. So that's a springboard for pre-stressed concrete. So what happens in pre-stressed concrete? Well, now we have an initial steel that is not passive anymore. Okay, so what we do is we provide the steel in there. Now, please remember, this steel is not a regular steel rebar we use in reinforced concrete. It's a very high strength steel, and these are typically not a single rebar. There are multiple rebars, and most of the time there are strands which are made of several different components. We call that a tendon. So in any case, so same beam, let's say simply supported, and then we have the steel inside. So what we do now is to stretch this steel. Okay, sometimes we stretch it before the concrete is cast. We call it pre-tensioning. I have a slide later on that. And sometimes we call that post-tensioning, where the tendons are stretched after the concrete hardens. So why is it beneficial? Well, if you can imagine, if this stretched strand is let go and anchored against the concrete, immediately the tension converts to a compression, pre-compression on the bottom of the beam. Am I right? So if that happens, then this beam suddenly cambers up. We call this a camber, which is really a upward deflection of the beam. That's typical of a negative moment. I'm sure you're familiar with negative versus positive moment. This one being applied on the bottom, it sort of applies a moment like this, which is a negative moment, and this beam cambers up. So this is before any load is applied except the self-weight of the beam, which is applied instantly when the camber develops. But then we apply all the other loads on the beam. You know, in case of a building, it could be floor live load in a building, or office building, or whatever. In case of a bridge, it could be vehicle load or other kinds of traffic load. So what happens now is that this beam now ceases to be passive. It becomes active, and the pre-stressing makes it active. So now you can imagine that this application of the load will first of all bring this beam to the neutral position, which is no deflection. After that, depending on the intensity of the load, the beam may go into a positive deformation like this. So the difference between the previous slide, where we had a lot of deflection, now the deflection will be much less. And in some cases, there may not be any deflection. The beam may still remain in a negative moment situation. So why is that useful? Well, now, because of that camber, pre-built camber, we have now the deflection going down much less when the load is applied. So bottom line is that we should be able to get quite a bit of more capacity from this beam. So why is that useful? Well, first of all, you can imagine that because of that pre-compression in the bottom of the beam, the concrete tension will be reduced. So the stresses in the bottom of the beam, bottom fiber, will be significantly reduced because of the pre-existing compression. So compression in the beginning, and then applied the tension, So bottom line is that addition and subtraction will make it less. So the tendons must be eccentric. Eccentric means that we don't want that compression to go to the centroid of the beam. You can, of course, you can make concentric pre-stressing, which goes to centroid, which in a rectangular beam would be at the center of the rectangle. But then it's much more effective if we apply eccentric pre-stressing. Eccentric means that you apply the pre-stressing off center from the centroid of whatever section we have, I-beam or T-beam or rectangular section. Okay. So because of that applied pre-stressing, we should be able to increase any kinds of capacity of the beam. For example, bending capacity, shear capacity, and also torsional capacities. And also, as I mentioned before, the surface deflection is reduced. Now, very important is the cracking part right there. So because of the reduction in tension, as we know, cracking in concrete beam is quite common, it's inevitable, and it's acceptable in design. ACI code accepts it as long as we keep it under check. So if you have wide cracks, what's the problem? Well, we have not really been able to really solve the corrosion of steel rebars in concrete. We have been trying for a long time. A lot of research has been ongoing. We have tried different things. Now in USA, we are using what we call epoxy coated rebars. That's supposed to give some kind of barrier on the steel reinforcement so that the corrosion potential is reduced. We are trying to use different kinds of concrete with some additives, using coatings and sealers on concrete surfaces. So why does the corrosion happen in concrete? Well, it's inevitable. Concrete is porous. It's not a solid material, especially in aggressive environments like coastal areas. In Texas, we have a long coastal area. We have a high temperature, temperate climate. Then we have salt in the air, salt in the water. And then with flooding and stuff like that, there is quick corrosion. So sometimes the corrosion happens within the first 5 years. I've seen bridges where a new bridge, after 5 years, had corrosion of the piles. And you can appreciate that how much difficult that is to rehabilitate a bridge which has corrosion of the foundation. It's very difficult. Sometimes the whole structure has to be redone. So with pre-stressing, we can control that cracking because the tension is going down in concrete. As a result, there will be less chance of ingress of any kind of corrosion producing material like water or salt or chemicals. And that should really decrease, hopefully, the corrosion of steel rebars, even pre-stressing rebars. And that will allow the durability to go up. And we add to the sustainability and the service life of the member. So here are some examples. This is from a precast yard. It's not too far from us here in Dallas. You can see here, this is a long line casting. Okay, so this is practice, and I always try to infuse practice in my lectures to professionals as well as my students, and they really enjoy it. That enhances their learning experience. So here, this is I-beam, typical I-section. We call it I-girder. AASHTO has standard shapes for bridges. Of course, other shapes buildings are from PCI and other sources. So this is a long bed casting. So what they're doing here is they have this beam. You can see the joint right there. So it's a long line casting in a precast yard. So in one shot, we can cast about even 10 beams, depending on the span of the beam. That's really effective. The strands are fed through the bottom flange. It goes all the way to the end and is stretched. This is called pretensioning. And then the strand is let go after this concrete hardens. Okay. So you can see the camber here. Easily, I can see that. I think this beam was about, we are used to in the US of the US system. So probably 100 feet or about 30 meters of length. So you can see the camber right away is very visible. It's probably a few inches here at the center of the beam. What's the virtue of precasting? Well, there are many virtues. Precast concrete is supposed to be better quality. Okay, It's supposed to have more control. As you know, concrete has many, many ingredients. Modern concrete has even 10, 15 ingredients in there. So how to control that mix? That's the big thing. How to control the curing, how to control the storage. So that's really helpful in a controlled environment like a precasting yard. So here is another beam, which you can see here. This is, as opposed to the I-beam, this is what we call a ledge beam. Okay. Why is it called a ledge beam? Because you can see the ledges on two sides, right? So you can see the pre-stressing strands here very clearly. If you can look closely, you'll see that these are not really one solid strand. It's made out of 7 wires in here. So typical, we call it 7-wire strand. So there are many of them here in the bottom flange. And this is used typically in a building where there are floor beams which come from the side and they rest on this ledge beam here. Okay. Very simple construction. The floor beams are simply supported, while these can be simply supported or they can be continuous. So you see here, if I'm in a classroom, I would ask the students, what's going on through these pipes? Some of you may know, right? So these pipes are feeding steam onto the member. And typically once the steam is released, it's covered by fabric. So this whole concrete is steam cured. What's the advantage of steam cured? Well, we know the hydration of cement is very important in concrete. Okay, the more the cement hydrates, the better the strength. So typically moist curing is done about 28 days. The steam curing can cure the same amount of cement in about 24 or 48 hours. So this whole curing process will be done in 2 days. What's the advantage to the precast yard? Well, they can release these strands and they can remove them on the side. After 2 days, 3 days, they can cast more members. So these are all businesses. They're trying to make money and serve the communities. So by doing that, they can produce many, many more beams in 28 days or 30 days. So they're stacked on the side. You can see the steel formwork here, which is right there. Granted that pre-stressing can be done in cast in place or precast. Okay, both systems are useful. So these steel forms are usable, reusable, and they're reused, they're moved, and this operation goes on. You know, these yards in US are very, very busy. Sometimes they're booked year in advance because of all the infrastructure developments going on in the USA. So let's talk a little bit about pre-stressing reinforcement. For regular reinforcement, we are used to lower strength. Okay, for example, 240, let's say 420 megapascal. Okay, which is typical. In USA, we call it 60 KSI steel. But if we use pre-stressing steel with that strength, that will not really work because we need to stretch the tendons quite a bit. Okay, so not unusual to see the tendons stretching by multiple feet. Okay, 2 or 3 feet, because we have to have that force develop in the tendon and then applied back onto the concrete. So typical strengths are very high, 1860 or more megapascal. Okay, and also other problem with the low strength steel is that as we apply the pre-stressing on the steel, it inherently will lose stress with time. Okay, we'll talk a little bit about losses today. I'd like to mention that pre-stressed concrete is a vast subject. Okay, I teach here at UT Arlington a whole course, a semester-wide course on pre-stressed concrete, which is taken by undergraduates as an elective and also graduate students as a required class. Now, you can easily imagine how difficult it is to squeeze that into a 3-hour lecture. So that's why what I'm going to do in this class I'll give you some flavor of different parts of pre-stressed concrete, fully knowing that I will not be able to cover all the details of pre-stressed concrete in there. Hopefully you have sufficient knowledge that you will retain and apply either in your job, or if you take the structural engineering exam, maybe you'll be prepared for that exam to this lecture. So I will talk about losses a little bit. So with time, there will be losses. Some losses will be appearing immediately when the pre-stressing is applied. And some losses will be over the life of the structure or 5 or 6 years. So because of that, because to offset that loss, we need to use this high strength steel. So that's something to remember. There are different kinds of losses, and I'll talk about that. So these are the different forms of pre-stressing reinforcement that are available. Now there are stress relief wires, there are stress relief strands, and high strength steel bars, Davitec bars. So nowadays, question is, do we have to use steel? No, not necessarily. As you know, the composites are available now. There are reinforcing bars made of CFRP or GFRP, and there are also pre-stressing tendons that are available in composite. So that's available. So the advantage is that the composite will hopefully never corrode. They cannot corrode because they are non-steel. There are some thoughts that they may degenerate with time. The composite may degenerate, but that's a different issue. So the corrosion potential is wholly removed. So one advantage of the composite reinforcement is that the cost, life cycle cost, right? We talked about durability and sustainability of the structure in the previous slides. So we should not really look at the initial cost of the structure. So if you think about the cost of steel rebar versus composite rebar, well, of course, the steel will be much cheaper because steel is widely used and is widely produced. So with time, hopefully the composites will take hold and the price will go down. Composites are quite a bit more expensive than steel right now. But if you look at the life cycle cost of the structure, it's a no-brainer because in a structure, in an aggressive environment, if you have to repeatedly intervene, and if you have to apply intervention like rehabilitation, repair or inspections and other things, or even replacement, that simply may not be cost effective on the long run. So you need to look at the cost benefit ratios, and from that angle, composites make sense. But there's something that the designers or owners can decide what kind of steel to use. Just enough to say here that composite pre-stressing steel is available for us to use. So I talked about the two types of pre-stressing systems. Well, one is pre-tensioning and one is post-tensioning. There are structures where they're hybrid. Okay, the structure can be partly pre-tensioned and partly post-tensioned. I will talk about that a little bit later on. Or the structure could be wholly pre-tensioned or wholly post-tensioned. Sorry, somebody's calling on my Teams phone here on the office. I apologize for that. So here are some points on the pretensioning. So in pretensioning, as I mentioned before, we have fixed anchorages. So we have anchorages, bulkheads on the sides. And then before the concrete is cast, we place the tendons there, then we stretch it, and then we anchor it against the bulkhead. So you can imagine that the tendon is still in tension. It is normally done at a precast yard, which is really cost effective in terms of the management of the casting and also the storage and transportation. Or for large jobs, it can be done on the site. Okay, it's not unusual in the USA for large bridge projects to have a temporary precast yard set up at the bridge site, which really cuts down on the amount of transportation that is done. Especially you can imagine if a precast member is 150 feet long, it's very difficult to transport it. Okay, if it's near a waterway, you can use barges to transport it, but on the highway turning can be a big issue. So several elements may be cast, as I mentioned before. You can do long line casting. And other thing is that you can do exotic thing with the strands. So if I have only simply supported beam, It's all under positive bending moment, so I don't have to vary the profile of the tendon, but I can vary the tendon profile by trying to address the negative moments in continuous structures. So one issue is that we must be very careful when the stress is released. That's very important for concrete, pre-stress concrete structures. The photograph I showed you of the precast yard. Now, if after steam curing, the stress is released, pre-tensioning is released after say 2 days, sometimes we forget that the concrete is very green at the time, right? When we talk about F prime C, the design concrete strength, which is typically in the as-built plans, we can say, well, that's a 28-day strength based on STM testing of 3 cylinders. But the strength at the time is not what you have in a green concrete in 2 or 3 days. So that property we call F prime CI, the initial concrete strength, which could be quite a bit less than the 28-day strength. So if I design a structure where the stress is released at the early concrete strength, I must be careful to use that strength and not the design strength, which is down the line on 28 days or so. That's something very important, because otherwise there'll be a big mistake and our design will be non-conservative. So here is the artist rendition of pre-tensioning, where we have the anchorage on the sides. We have this pre-stressing is applied to jacks, as you may know. Okay, so what the jacks do, they stretch it. Okay, they stretch this tendon here, and the way to measure the pre-stressing force is interesting. Okay, there is no meter. We just measure the elongation of the tendon, and there's a calibration chart. Okay, if this is elongating by 500 millimeter or whatever, then what's the corresponding force in kilonewton? So that's known from the manufacturer. Okay, so that's what we do. It's a very simple process. I have some photographs. I don't have them here in this lecture. I probably will include them in my bridge lectures later on, where you can see how people are measuring this. Now, this is very, very, very risky practice. So I should not laugh, because people have been known to lose their fingers because somebody standing operating this jack here, and suddenly this strand breaks, and strands can be defective. So there may be some defect in the manufacturer. So suddenly this flies at high speed, and there are injuries to the people standing here. So that's very difficult, very risky practice, staying nearby this. And I'm sure the precasters take proper precaution, and there are liability issues that are addressed. Anyway, so once it's stretched, and then what we do is we just anchor it here. Okay, it's already anchored on the other end, and it's anchored here. Now you can imagine that's under tension, and now we have this concrete cast. So this is bonded. That's why we call it a bonded reinforcement, because the concrete is laid against the bare steel. So it immediately will bond, and the bonding will grow with time. So at some point, depending on the curing of the member, we will let it go. So we use a blowtorch or something to cut these strands, and immediately this will go into camber. So this is what we call a straight tendon. That means that the tendon's profile is same. The beam centroid will be somewhere here, depending on the symmetry of the beam. So from that point on to the tendon, we call it the eccentricity. It's typical eccentricity. The language is same for footings or whatever, or columns. So that will give you the negative moment that you desire. So one thing I like to mention is that because of the fact that you release it here, this beam is wholly under positive bending moment for a simply supported beam. Maybe I'll talk later on about that, but there's a potential for tensile stresses to develop at the top of the beam right here, where there is no other moment. So when I apply the dead load and live load, the maximum moment will be at the midspan, typically for a simply supported beam. But over here, the moment is almost zero or non-existent. So only moment will be acting at the end would be the negative moment from the pre-stress. As a result, this stress can be quite high, And that's why SCI code asks us to limit these stresses. Otherwise, there may be unwanted cracking on the top, and there could be durability issues on the beam. So here is a variable tendon. The first one we saw was a constant eccentricity tendon. Here's a variable eccentricity tendon. So what we do here is that we have hold down devices. So this is a hold down device, that's a hold down device, there's a hold down device. So we determine what kind of eccentricity we want. Okay, now why is this variable? Let's see what we try to do here. So what we did by doing this, we reduced the eccentricity here, right, on the end. Remember what I told you in the previous slide, that because of the lack of any other applied moment here, there can be tension on this upper part of the beam. So by reducing the eccentricity, by using variable tendon, we can drastically reduce the cracking potential. You can even feed it to the centroid of the beam here so that there'll be no moment at all at the end, and there'll be no chance of any kind of tensile cracking on the top of the beam. And this is easily done in a precast yard. To do this, it can be difficult to do it in the field, but in precast yard, it can be easily done. So long line casting, so it's the same logic, beam 1, beam 2, beam 3, and so on, even beam 10, for big yard, there can be 10 beams. So they are laid longitudinally, very efficient system. The same tendon goes through all of them. There's a little bit of separation here for cutting the tendons, but it goes in here. The strand is fed through here, and then jacking is done. The same force can be applied. You don't have to increase the force because the force is constant to the strands. It's anchored here, stretched here, and then once the beams are hardened, we cut it here, cut it here, cut it here, and cut it here. All the beams will go into camber, and then they can all of them could be cured, and then they can be placed in service or transported or whatever. We call this a long line casting or stressing. As opposed to pretensioning, post-tensioning is done on hardened concrete. So instead of having the strand bonded to the concrete, what we do is we place, let me see if I can move this around a little bit. Okay, there we go. Is that better? I hope so. So that it doesn't obscure our views. Maybe I'll put it here. Okay. So strands placed in ducts. So what we do is we place empty ducts. So it's like a conduit. It can be made of steel. It can be made of plastic. So they are placed in the formwork ahead of time of the concrete being poured. After that, we apply the concrete. We cast the concrete around the duct. Now you can imagine that there's an empty duct going to the concrete. There's a void to the concrete, and we can even vary the profile of the duct to conform to the moment diagram. So once we apply the concrete, it hardens. Then what we do is we feed the strands through the duct. So it goes all the way from one end to the other end, and then we anchor it on one side, and then we apply the pre-stressing from the other side. And then there are grouting ports into the ducts, and we typically grout it. Inject grout from one side of the duct. The grout comes out on the other side, so we know that the conduits are fully grouted. So it gives you the bonding that we desire. So here is another artist's rendition of post-tensioning. Here is the concrete beam. Post-tensioning is typically done in the field. It's not done in the precast yard. So we have the anchorage here, and then we have the jack. So this is a variable tendon profile. So it's noticeable that we have a parabolic profile of the tendon here. So we anchor it here and we jack it on the side. This is the conduit showed in dotted lines or dashed lines. After we apply this, the pre-stressing is applied onto the concrete. As a result, you can again have the camber in the midspan if you desire, and then the loads will be applied and the beam will react accordingly. Sometimes there are intermediate diaphragms for the beam. If there are voids in the beam like this, the tendon can still be fed through the different parts of the beam. And then we can stretch the jack, the tendon the same way. And then we're going to have the desired post-tensioning in the beam. This kind of stabilizes the beam. And if you need to reduce the dead load of the structure, this is a convenient way of doing that. So here's a case of a continuous beam, which is one reason why we do the post-tensioning. So this is a cast-in-place beam, two spans, 3 supports. As we can imagine, this is a continuous beam. Depending on the end condition, there could be end moment. Now for this hinge support, there'll be no end moment, but we can guarantee there'll be negative moment at this intermediate support. This can be a bridge member, it can be a building member where we have continuous span. It can be multiple spans, more than 2 spans. So no moment here for these hinge condition, but there is negative moment here, right there. And as we know, in the midspan area or near the midspan, there will be positive moment here on this span and positive moment here on this span. So the trick here is, designer, we have to address those moment curvatures or the moment profile, because we'll try to use the post-tensioning to effectively give us the resistance against those moments. So what we do is we can use easily a variable profile. So what it does is that you can see here that the steel is bent down here. So it's below the centroid of the beam. So it's going to give us a negative moment, right, at this point from the pre-stressing, which will react against the positive moment from the loads, dead load and live load on the slab. Makes sense, right? Now here, because of the negative moment, you like to have the eccentricity reversed. So here is the centroid of the beam here, and here is the steel. So that would be our eccentricity. That would give us a positive moment, post-tensioning, and that will again address the negative moment here. Same thing happens here. So it's an imaginative way of doing that, quite common. Okay, if I use the straight tendon here, what will happen? Well, that's a tricky question, right? I could ask my class today after this lecture. So if I apply a straight tendon here, which will be easy to cast, easy to construct, well, that will work for the positive moment, am I right? But unfortunately, that will not work for the negative moment, am I right? Because I'll still be producing a positive post-tensioning moment here, negative moment, which will be adding to the load negative moment here. So that would be counterproductive here. Okay, if you have any questions, just post them on the question and answer, and I will try my best to answer them after the end of the lecture. So with that little bit of introduction on the pre-stress construction, let's go into the design equations. And some of these are simple and some of them a little bit complicated. If I've taken them from the ACI 31808, the SI version, the number will be shown against the in a parenthesis next to the equations. And if you have a copy of the 08 SCI 31808, you can go back and check them out. So as I mentioned in the previous slides, the stress is very important, right? The stress in a pre-stressed member is very important, especially on the tension side. Not only that, the compression side is also important. Although concrete has reasonably high compressive strength, you don't want that to be exceeded. So these are the basic equations, which is not from SCI code. This is from mechanics or statics, maybe mechanics of materials. Let me explain these three terms. This is the axial stress term. You understand, right? P over A. So that's the pre-stressing force divided by the area of concrete. I have used negative sign as compression. Some people may use positive for compression, but I typically use negative for compression. So we understand that's uniform stress on the cross section. Next would be the moment from the pre-stressing. How does it work? Well, let's see. The pre-stressing force times the eccentricity gives us the moment, easily understandable. And then the centroidal distance to that point and divide by I will give you the bending stress. Am I right? Very simple. It's called, in mechanics of material, we call that MC over I. Very well-known equation. And we see the use of mechanics or statics in concrete by using this kind of equations. So why is this positive? Well, this moment will cause positive stress in the bottom. Okay. Sorry, negative stress in the bottom because it's let's see, this is a negative moment. So positive on the top, tension on the top, and compression in the bottom. So looking at the top stress, that's why this is positive, because it's positive stress on the top. And this is the applied moment. So this moment here is applied, is through all kinds of load applied, self-weight or overlays or live load. So that moment I have summarized it here, same equation. And why is this negative? Because that's the positive moment typically. So that will cause negative stress. This is the top stress overall in the pre-stressed member. And then this is the bottom stress. Let's try to understand. Now this sign reverses here because bottom, and this sign also reverses because now it's in the bottom. Hopefully you understand these equations because SCI imposes stress limits, okay, to try to make the members more efficient, and this is the way to find those stresses. So as I mentioned before, high tensile stresses may be caused, especially in simply supported beams. So we have to be careful in designing those kind of members. And also, as I mentioned before, drape tendons may be used to address those high stress issues. So we are gradually going into a little bit complicated stuff here. Here is the beam I showed you before, which is, now you know that this here has a constant eccentricity tendon right here. You can see it right there. Okay. That's the eccentricity. Now we understand that's the pre-stressing force applied. And because of that, this one just shows you the same equation I showed you before, P over A, which is the uniform stress on the cross section, then P C over I. If it's only pre-stressing, this would be the net stress, right? These will again work against each other. It will reduce, and these will add. So this will be a kind of a trapezoidal stress distribution on the section. So this is only pre-stressing, nothing else applied, which is hypothetical because you can easily imagine when the pre-stress applies, what happens? Immediately the member cambers up and the dead load self-weight takes effect. There's no way to avoid that, especially if you are supporting at the end. So it's instantaneous. The moment pre-stressing is applied, there will be downward load from the self-weight. That's shown on the next one. So here we have self-weight added. So now what I've done is I've taken that trapezoidal shape from before, okay, which was the pre-stress effect only. Then I've superimposed the dead load, not the dead load, but the self-weight stresses, which for a symmetric member would be same. So this is MC over I. Now this changes, right? Because now we have this one adds to that, and this one goes down because this is a reverse stress here. So at the bottom, we can end up with tensile stresses as well, right? which may not be desirable, but we can accept some limited tensile stress at the bottom of a pre-stressed beam. So this is the condition which happens after pre-stressing transfer to the concrete beam. Now let's think about the life of the structure. I always believe in looking at the sequence of loading on the structure. It's very important. Sometimes as a designer, we forget that the loads are not applied at the same time. There can be lag in the loads applied. So let's think of this life of this beam here, pre-stressed beam. This has been cast, and it may be lying somewhere, in a precast yard on the side, and it's not unusual to sometimes have them stacked up one on top of the other, because in the yard they're trying to save space. If it's at the site, it's probably being placed in service. So from the precast yard, we'll be moving them to the job site, at the building or a bridge, or at the temporary site, we'll be putting them up. So once they're placed in service, what happens next? Well, if you think of a bridge again, so here's a bridge, and we place this member on the bend caps. Okay, the bend caps are the ones which supports the beams. In a bridge, we call them bend cap or pier cap or bend sometimes. So once it's placed there, then we typically will place a deck or a slab on top of that. Same thing can happen in a bridge or a building, unless we have members where the slab is already cast together with the beam, like a T-beam or an I-beam or something like that. So with that, then next loading stage would be the self-weight of any additional attachments like slabs or decks or floor finish or something like that. And then we're going to go into the live load. So all these sequences may happen immediately, not immediately after this part. It will not happen immediately the next day. It may take, sometimes it takes a few months for going from here to the next stage. So here is that beam I showed you before. Now it has rained, which is helpful for the curing. It probably doesn't need any because it has been steam cured. So we can see again the long line casting here. Okay, and we see several strands. I like to point out that this is very important, the placement of the steel and the constructability of it. ACI addresses that, as you know, through providing covers, minimum covers for concrete, and then also providing clear spacing between rebars or layers of rebars. Now, we should not use the same values for pre-stressing. They're quite different, and I like to point out that in ACI there are separate values for pre-stressed concrete, which is different, most likely is lower than reinforced concrete. I showed you that same photograph before. Here is the post-tensioning beam. Interesting, post-tension beam. This is being cast here, and you can see clearly that the ducts are here. Okay, these are metal ducts. There are ducts in the bottom here. There are ducts here, ducts there, and ducts there. You can easily see the profile of the tendon going up from here, which was in the bottom, which I showed you in the drawing before, and it's following the moment curvature of the beam. So over here, I'm imagining this will be a support where there will be negative moment. So this one is trying to address that by varying the profile of the tendon and providing you with a negative eccentricity from the centroid of the beam. And you can easily see the shear reinforcement, which goes all the way up there. Most of the time, they are sticking up from the beam because we need the dowel action that would be needed to make the deck or the slab composite with the beam if it's needed that way. Also like to point out, these are, you may know, these are called hold down, these are called lifting devices. These are made of cables which are embedded in the concrete. And if we need to lift that, we'll be lifting it from here upward. That's a tricky issue. And again, the designer should be aware that where should we lift it? It's a very, very critical point. If it's simply supported beam, you want to lift it a certain way, and that may cause unanticipated stresses. Okay, although it may be short or transient, because you're lifting it and placing on the side or placing it on a truck or barge or whatever. But if I'm not careful about anticipating those stresses and providing mild reinforcement at least to control cracking, that member may be in trouble. So that's good to remember that. So now coming back to the equations. So after the beam is put into service, we consider a total moment. So as I mentioned before, it's in service. So this is a condition where the beam has been placed into service. Everything has been placed. Okay, the structure is complete. So the moment on the structure now would be the summation of all the moments, right? This is the external moment applied, not the pre-stressing moment. So the total moment would be the dead load moment or self weight of the beam or the slab or together. This is the superimposed dead load moment, and this is the live load moment. So it all depends on the support condition of the structure. That will dictate the moment, the values of the moments, and then also in load factors that has to be applied for concrete design. So the load factors are interesting. I think Dr. Ghosh may have covered that in the previous sections of this lecture series. So the load factors do not depend on whether the member is reinforced concrete or pre-stressed concrete. So that only depends on the type of load you have. And as you know, there are load combinations in SEI, which are statistics based. We typically use those factors and wisely look at load combinations that we have to use. For example, I can use for a bridge. Of course, SEI doesn't apply for bridges. We use AASHTO code for that. But we have to use what proper combinations. Okay, do I use flood load? Do I use seismic load? Do I use wind load? Or do I use all of them? If I use all of them for extreme events, then I must use a reduction factor, because the chance of all the extreme loads happening at one time, or all the maximum loads happening at one time, is quite remote. So the same philosophy applies here, no surprises here. So I like to point out here in this equation that the difference between the previous PI that I mentioned, which is the initial pre-stress, which was applied at the beginning of the structure's life, now has been reduced. So typically in pre-stress design, we call it effective pre-stress. So this has been reduced by losses. So as I mentioned before, losses are unavoidable in pre-stressing steel. It will happen, and I will cover that in some of the slides later on in this lecture. So that's reflected here. How much to reduce? Sometimes we use detailed calculations, and sometimes we use what we call lump sum losses for pre-stress. So what this has done, it has summarized everything. This is the top stress in the beam. This is the bottom stress in the beam. And I have placed this in this convenient form. So instead of using that MC/I form, I have used the R square form. And you may know that R stands for radius of gyration, which is a convenient expression which summarizes the I and A values in the beam. So this has kind of simplified the equation, and we can use these equations as well if you want to design for stresses in stress beams. And this is the total moment. Now I have done also what I have done. I have replaced I over C with S, which is the section modulus. So this is the top section modulus, and that's the bottom section modulus. So you can appreciate, suddenly this equation looks a little bit simpler. Instead of using the longhand I and A values, I'm using R, radius of gyration, and I'm using section modulus. As I mentioned already, we need to be very careful about intermediate loading conditions. I can't emphasize that enough. In a pre-stress concrete class I teach, I say, look, students, don't look at the initial condition only or the final condition only. Look at the whole life of the structure, especially for pre-stressed members are not unusual to cast it on one place and move it and put it in service. It can also be done cast in place in service to start with. So think of that. If I have a precast member, it's being transported and we're transporting on a truck. So it's sitting on the truck bed, and here the truck is going on a rough surface at high speed, and there are vibrations. The beam is being moved around, is being vibrating. So vibrations are not very good for concrete structures. So the vibration may cause additional cracking. It's very difficult to account for that in design. But at least the designer should keep in mind that this kind of situation may happen. I mentioned the lifting before and the unintended stresses it can provide. Construction load should be considered. So this is another big issue. So I have been to many building inspections in USA, and I've seen multiple story buildings where the contractor was forming up the slabs. So they have been using scaffolding all throughout. So here is level 1, floor 1 scaffolding, slab being cast. Here is level 2, floor 2 casting, and the scaffolding is there. And after 7 days, the contractor needed the scaffolding or the formwork. So they removed that bottom story scaffolding. Again, that's risky because the concrete is still green, right? It doesn't have the full capacity. So did the designer consider that in design of the floors? Who knows? Typically, that's not done. And typically, it's not unusual to have the floors stacked up with material, construction material, bricks, masonry units, cement bags, bunches of rebars, construction equipment. Not unusual, okay? So how does it affect our structure? That applies to any kind of structure, timber structure or steel structure or masonry or concrete. So again, we cannot really anticipate all kinds of loads. It should be good to limit those construction loads on structures. We have the fee factor and the load factors, which gives us the safety, but do they account for all these unintended effects? I don't know. I don't think so. For example, the fee factor for design is only 0.9 for bending, which is only 10% reduction. That may be offset by all these other unintended loads. Just to keep in mind that can happen, and have good construction practices to control those kind of situations. So now I am transferring from rectangular beam to an I girder, trying to go to the real type of pre-stressed beams. Typically, when I teach concrete, I tell students that, well, here's a rectangular beam, okay? Here's a rectangular beam, here is the stress block, here is the reinforcement, here's the A value, here's the VW and stuff like that. But don't expect a rectangular beam to be in practice, which is true. Most pre-stressed beams are not rectangular. They are shapes like this. This I girder, typical Astro girder for bridges. These are unequal flanges, and there are sloped sides because that creates easy removal of the formwork. It doesn't stick to the concrete that much. Of course, we use form oil on the formwork to prevent or minimize those kind of addition. So here is the stress again, right? Before losses, the constant force on the pre-stressing, the constant stress, then variable. So here, instead of ending up with equal stresses, we have unequal stresses. Why is that? Because this member is not symmetric, right? Cannot be symmetric because the top flange is heavier than the bottom flange. So the CT and CB will be unequal. Okay, CT will be this much and CB this much. This is eccentricity that's defined as from the centroid of the pre-stressing to the centroid of the cross section. So we need to understand that stresses may not be equal, and you may have to calculate them separately to check the stress limits from ACI. addition of self-weight. Now we understand that we are progressing now to the different loading stages. This was the previous with only pre-stressing applied. Now it's self-weight. And suddenly we have this situation where we have unequal stresses, quite a bit of non-uniformity on the cross-section. Now this is service load at effective pre-stress. So the pre-stress has been reduced by the losses. And then we apply the other loads on the structure. Suddenly we have a little bit of improvement in the condition. So this stress has been reduced a little bit, and this stress has been also changed. So that's why SEI applies stress limits. There are two kinds of stress limit. One is for the initial condition, and one is for the service condition. They are different, and SEI indirectly recognizes these kind of situations to those stress limits. So now we can fall back onto SEI code 18.4. If you have it, you can look into the SEI code if you have a copy of that, or you can look online. I found SEI 318.08 metric online, okay, and it's available. Initially, I was trying to buy it from SEI, and it was quite a bit expensive, so I got it kind of free. Google is our friend, right? So you can get all kinds of stuff on Google. So here is the stress F prime CI, as I mentioned before, compressive strength and initial pre-stress. Now we understand. Please be familiar with this nomenclature, this subscript. I means initial, and F prime C is the compressive strength at service. It makes sense, right? So SEI gives us, as I mentioned, the limit. Very important, okay? This kind of stress limits are not in the regular reinforced concrete in the SEI code. They are only in pre-stressing because of the fact that pre-stressing can drastically change the stress situation depending on the support condition and the eccentricity. So if the specified stresses are exceeded, SEI asks us to use bonded auxiliary reinforcement. We must provide additional steel reinforcement, which is mild steel, which is supposed to supplement the pre-stressing steel. And it's supposed to address all these unintended stresses that we need to control in pre-stressed members. So these are the stress limits. By now, you are, I'm sure, or hopeful that you understand the difference between transfer and at service load. Again, to repeat myself, transfer means initially when the pre-stress is transferred, and at service means in service when all the loads are applied and the member is in service. SEI does not recognize the intermediate load cases, as I mentioned before. So in compression, limit is 0.6 F prime CI anywhere. So if you have a compressive stress, this is the limit. And as I mentioned, F prime CI is the initial concrete strength. We collect cylinders at the initial stage. Actually, we collect cylinders, doesn't matter what stage, it has to be during casting. And then we test some of the cylinders initially, depending on when the pre-stress is released. If it's steam curing, we have been doing it at 2 or 3 days. And then we test the rest of the cylinders at service, which would be 28 days typically. At end of simply supported members, this is the limit, 0.7 F prime CI. Now these are in metric, these are in megapascal. Of course, if I using the US system, that would be in KSI, but that's the different factors applied. If I'm looking at tension stresses, if we exceed 0.5 square root of F prime CI at simply supported members, or 0.25 square root of F prime CI other locations. So I'm interpreting this as meaning that this could be for continuous members where tension can appear at other locations besides the end of simply supported beams. We must provide bonded reinforcement, as I mentioned before. So that will hopefully address any kind of serviceability issues, cracking and durability issues. At service load, in compression, this is the limit. We look at pre-stress plus sustained load, and the limit is 0.45 F prime C. In compression, I think this should be in tension. Sorry about that. No, sorry, this is in compression. I was confused for a second. In compression, this is a total load. So difference between this and that is that this is the sustained load, which means, what does sustained load mean? Well, kind of confusing, okay? Pre-stress is always sustained, although it's reduced a little bit, but at the end, but sustained load here typically would be meaning dead load, right? So the self-weight, any kind of permanent load, attachments that are always there, or most of the time there. Total load, what do you think total load would include? That would include the live load as well, or any kind of transient load that will be applied on the structure. That limit is 0.6 F prime C. So designing these, as I mentioned before, this lecture, there's no way I can cover all the details. In a design, you'd be checking stresses. So the way to do that would be you find the stresses based on the equations I gave you, and then you check against these. So suppose the stress limits are not satisfied, which means is that the stress you calculate is more than the limit. What do I do? Well, one option is to add auxiliary reinforcement for tension. In compression, there's no other way. If I'm exceeding the compression, I must do something. Doing something means what? Intervention in the design. I can increase the concrete strength if that's okay, or I can increase the cross section. That will increase the effect of the section, and that will reduce the stresses. Changing the support conditions is difficult. Changing span is difficult once the architects have finished their job. So those are the viable options, looking at the concrete strength or the section. Now, typically I've been finding from my practice that this value, the F prime C and FC, these are the as-built, whatever you get from as-built. For example, if they give you a value in the as-built, you'll find out that if you do the testing cylinder, they're typically quite a bit more, which is a good thing. Typically, we have been finding that the actual cylinder strength is about 30% more. Contractors are very careful in this regard, okay? Because in USA, if the contractors do not satisfy these kind of limits, they're in trouble. They have to pay a fine if they don't meet the strength requirement or slump requirement or air content requirements. Actually, we are moving more into performance-based design. We are thinking of including durability and sustainability in the contractor's checklist, but that's still under works. So what I mentioned to you before was the stress in the concrete. So SAI also imposes stress limits on the steel itself because you don't want the steel to be overstretched. Am I right? There are limits on the steel stresses. So here are the limits. So these are expressed in terms of these two factors. You may be aware of those. The steel has a yield strength. In reinforced concrete, we call it Fy. Or if I'm using bonded steel, we're going to call it same thing, Fy, but SAI adopts this subscript P for pre-stressing. So yield point is a critical factor in reinforced concrete design. Although there is a strain hardening in the steel, we typically ignore that. Now the pre-stressing steel is much stronger, so it will be a little bit more more brittle. So the strain hardening and the yield point may be a little bit more, may not be that well defined. But in any case, we know that from the manufacturer, and FPU is the ultimate strength of the steel. So knowing these values, these are the limits. This is from SAI code. This is section 1851. So due to pre-stressing steel jacking force, which is very beginning, you are jacking at that time, this is the limit, 0.94 FPY. but not greater than the lesser of 0.8 pu, and so on, for immediately after pre-stress transfer. So this is jacking. So immediately there's some loss. You can appreciate that because there'll be some slippage. So at pre-stressing transfer is 0.82 fpy, but not greater than 0.74 fpu. And in post-tensioning tendons, at anchorage devices and couplers, immediately after force transfer is 0.7 fpu. So why are these values like this? If you go to the SI code, as you know, there is the left column are really the code provisions, and the right column are the commentaries. So I'd advise you, if you want to know, if you're curious, you have a curious mind to say, oh, I'd like to know how they got these values. Most likely they will mention that in those commentary. And as a matter of fact, AASHTO tried to do something similar. I look at AASHTO specifications in my bridge lectures later on in this series. So why are higher stresses justified during jacking, which is 0.94 versus 0.82? Because we know the stress very well at that point. Okay, because we are reading that. You remember the deformation I mentioned, the elongation. We're reading that accurately, and we can pretty much predict what that value is. So why are there no limits? The question may come on the final service stresses. Good question, right? These are all initial conditions, because the thought is that at the end of the day, at the service condition, the stress will be lower in the pre-stressing, right? And there's no need to check that because these are okay. Hopefully, those will be okay as well. Now, transitioning from rectangular to other shapes. So I always tell my students, they ask me then later on, why are we doing rectangle? Okay. Well, as like reinforced concrete, if we don't do rectangles, then we're in trouble because all these shapes are combination of rectangles. As you know, reinforced concrete, we do these kind of things. So transitioning from here to an I-beam, or this is a symmetric I-beam. This is a non-symmetric I-beam. This is a crazy beam, right? Non-symmetric in a different way. This is a box girder. The other shapes, we use double T beams pretty regularly in the USA for parking garages and stuff like that. Very efficient section. One reason is that the flange attached to the double T becomes your slab, and there may not be a need to cast additional slab. While here, in these situations, you have to cast a slab on top or a deck for a bridge. That has to be composite. So you have to have dowel bars sticking out from here, which can be done. It's not very difficult to do, but that needs additional work and additional cost involved. So there are other shapes I haven't mentioned here. In USA for bridges, we're using U-beams, which is very efficient. And then there are other kinds of beams. Actually, in USA, there are very tall bridge girders that we're using, which can span up to 300 feet. Amazing. So one issue with the box is that if you're thinking of torsion, which is very common for any kind of pre-stress beams, this is more torsionally rigid than these open sections. So for ramps, for example, on a bridge, which typically would have a torsion applied, we typically use a box section to efficiently address that. Now, when you start designing pre-stress concrete, sometimes you grope in the dark. Okay, what shape should I use? Okay, should I use I-beam or a T-beam or double T-beam? One-way solid slab, hollow core slab, or two-way solid flat plate? I'm sure you know the difference. One-way solid slab versus two-way slab. I think Dr. Ghosh may have already covered that. Then hollow core slabs are slabs precast where the core is hollowed out. Very common in the USA for office buildings and hotel buildings where you can try to reduce the self-weight. One issue with concrete structures is the dead load. Self-weight is quite high compared to steel or timber. So anyway, we can reduce the self-weight. It's economical for us. Flat plate means, as you know, there are no beams applied, or maybe there may be column capitals or stuff like that, and there's also flat slab. So from practice, these are economic span to depth ratios. This is based on practice. So if I'm using double T beams, the economic span to depth ratio is 30 to 40, bridge girders 25 to 30, and so on. So this is what we call a preliminary design. Before you start designing it, architect gave you the drawings, then you need to figure out the size based on the span length, and this gives a guideline. It's not cast in stone, but that's a good starting point. Doesn't mean that I can't use something out of this range, but that may not be the most economic. So what we do is then we select the shape. When we select the shape based on the span depth ratio, which is done for buildings as well as bridges. Okay, in the bridge I will cover how to do preliminary design, how to select the shape for a bridge girder, and then how to economize the design. So we select a trial section. So you have to start somewhere, right? You cannot just start blankly. So a trial section means what's the shape, what's the size of that member. We select an F'(C) based on practice. Then we limit the top section modulus and the bottom section modulus. Then we have to modify the section. Typically for any design, it's an iterative process. So we go through this iteration, maybe 1 or 2 or 3 iterations, which can be quickly done through spreadsheets or software. So it's an open-ended problem. And you may have at the end 2 or 3 different designs. Then you select one based on your preferences and also the availability of material and other factors that may affect the construction. Very important. I mentioned the steel protection before. So here are the provisions from ACI code 31808. So this is section 7.7. Again, I invite you to visit that section if you're trying to design pre-stressed members. And please don't use regular reinforced concrete, which is actually the same. I think it's in the previous section. The covers are given for regular reinforced concrete. Oh, sorry, let me go back here. So there are 2 tables which I'd like you to pay attention. This table is for cast-in-place concrete pre-stressed, and this is precast concrete, which I mentioned before, manufactured under plant control conditions. So here are the different exposure categories, which is quite common in reinforced concrete design. If you have concrete cast against permanently exposed to earth, 75 millimeter here. And look here, okay? Look at how the values are dropping. So value dropped from 75 millimeter here for cast in place to 40 millimeter here for precast. What happened? Well, this is easy to guess. As I mentioned before, precasting has better quality typically, so it's more durable, so that we can relax the cover requirements. That's one advantage of using precast concrete. Now, if I reduce the cover, if I use the same depth member, my moment arm will go up, and as a result, my strength will go up. So I can optimize the design by allowing more load on the structure, or I can span it longer, right? So those are the virtues of using lesser cover. Cover is there for a reason. We shouldn't compromise that because that's there for the durability. Okay, I tell my students, use minimum and use more if you can. There are ways to avoid these by using additional protection on the structure. So I've been experimenting with carbon fiber wrap for a while now. So by putting those layers on concrete, that will give you the carbon fiber laminate does not only give you strength increase, it also gives you durability increase. I've shown through my previous research that the cover can be reduced by half if you use CFRP protection laminate on top of the structure. Now, CFRP laminate is a separate issue. It's used both in buildings and bridges in the US. mainly for rehabilitation of old structures. So it's still not very prevalent for new construction. Bodhi, should we take a 5-minute break now? It's about the midpoint.
We can take a 5 minutes break.
Okay.
Yeah.
So just stretch out a little bit. I know it's late in Bangladesh, 9:30 p.m. It's 9:30 over here. Have a meal or snack or grab a cup of tea and I'll be right back. Don't go anywhere. Hello, I'm back. So Bodhi, there is a request here for annotation. Are we allowed to do that or not?
Just ignore it.
Okay, I can decline it or ignore.
Yeah, decline it. Yeah.
Okay, thank you. Okay, welcome back to this second part of this lecture. So I mentioned the cover requirement is coming back. Let me see. Okay. So moving along here to the next slide. So this is the cover is one part of the durability aspect of the concrete, but then the minimum spacing is also important. So the clear distance between bars and strands should be the diameter of the bar or 25 millimeter, okay, whichever is larger. And that's also important because of the prospect of congestion of rebars and difficulty in placing concrete that can cause honeycombing and strength and durability issues. So at the end of pretension members, the spacing requirements are increased by ACI. These are all ACI provisions. I think this is from 7.6 here. Side. Okay, so please pay attention to that. And if you have ACI code, you can look at those pages. And if you are using bundling bars, bundle tendons, 4 tendons or bars is permitted, not more than that. That's probably more prevalent in post-tensioning than pre-tensioning. So I'll always like to look at the practical side of it. So here is a bridge under construction. We call this segmental construction in the US. So this is an exotic structure. It's a bridge under construction. You can see the segment here. What we do is these are segments. This is a hybrid structure, which is post-tension and pre-tension. So you can see this. These are the segments. So you can see the joints here. If you pay close attention here, there are joints, and this has a curve profile for the bridge. So what we're doing is they are being casted on the side, precasted, and these are transversely pretension in the flange. So the top is transversely pretension to give it some stability and strength during construction. Then we place them one against the other. They are match cast with the previous sections. Then we put them on here, balancing the construction, and then they're post-tension longitudinally. It's beautiful structure. By post-tensioning, you can make it long span. You can provide the moment capacity, and also you provide for continuous construction. So this is a structure where post-tension marries pre-tension, and we end up with a beautiful product. It's quite common now in the USA. There are very long spans being built with this kind of bridges. Also, I like to point out that you can provide curvature of the structure sideways by using the match casting of the segments. Building wise, well, here is a common construction. Here is a precast member, which is sitting on columns. So you can see here the double T's, which are precast and pre-stressed. They are put on the ledge beam, which I mentioned before. These are quite deep. And then the beauty of that is that you don't have to add any additional slab. It's already built into the structure. You can put overlay here if you want. Very fast construction. There are corbels on the column, which transfers the load from the ledge beams onto the column. So an SCI, as you know, SCI also has provisions for bracket and corbel design. And then the load is transmitted to the foundation. Very fast, very economic construction. Now let's change gear here. With the limited time we have, look at the loss of pre-stress. As I mentioned before, losses are pervasive. You cannot avoid loss. So if you can't avoid something, you have to live with it. Pre-stressing will lose stress over time. Approximately 5 years. Studies have been done and ACI has curves like that, which shows that after 5 years, the losses kind of level out. And if you provide for that in the effective pre-stressing, you should be in good shape. Now, I like to point out that although ACI and AASHTO have detailed calculation for losses, the different components of the loss, and you can spend all day on figuring out those losses, but they are very difficult to understand because there are many, many interrelated issues. For example, there is humidity in the air, there's temperature effects and interaction between them and the camber. It all makes it very difficult. And camber is very hard to predict. We can also try to predict camber, but it's very difficult at the end knowing what the real camber is. And I'll talk about camber in a future slide here. So most of the time, we end up using reasonable lump sum loss estimation. So it's not accurate, but they are conservative. To avoid, and of course, if you have a efficient computer program, you can do the detailed loss calculation pretty easily, but we can get away with the lump sum loss also with reasonable accuracy. So two kinds of losses appear. One is immediate during construction. So the moment you apply the pre-stress, the losses will be instantaneous. Then the other kind of loss we call long-term losses over time. That happens approximately over 5 years. So there are different factors that affect these two types of categories. ACI code does not have lump sum loss estimation. Okay, there's nothing there. There are other publications which address that. AASHTO has a table for lump sum loss. So the ACI code, as you know, is for building design, and AASHTO specifications is for bridge design. So we should intermix between them. And the Post-Tensioning Institute in the USA also has published such tables. So I'm suggesting that it's really up to you how you want to handle the pre-stress loss calculations. But these are guidelines that we can fall back upon. So let's talk about the individual losses. First one is very simple, elastic shortening loss. So what's happening here is that this is instantaneous, immediate loss. We have the member, the pre-stressing is applied, initial pre-stress, note it's immediate. Then the member shortens. Of course, the concrete will shorten, right? It will be compressed because of the pre-stress applied. So that gives us the basis to figure out how much is the loss. That means how much is that stress, that the strand giving in with the deformation, and how much loss is being applied. Relaxation loss, on the other hand, you can easily imagine this. If I hang a stretch of the strand, and with certain force, after some time, it will give. It's a property of the steel. With time, it will give. It will relax, and that's what is called relaxation loss. This is the ACI equation for relaxation loss. FPI, the factors involved. I think I showed this in an example that we'll talk about that later on. So I'm trying to just give you a flavor of the different losses and what they mean in the summary form. Creep loss, on the other hand, is due to concrete properties. So concrete has two kinds of properties that affect the loss. One is shrinkage and one is creep. As you know, creep is the effect on concrete of sustained loads. So if there are loads on the concrete for a long time, concrete will give. So that will cause loss in the steel as well. So you can see here, this is the ratio, the age versus CT over CU. Okay, these are time-dependent factors for creep. In the beginning, there's a little bit here, but then with time, it goes up and then sort of flattens out at about 5 years of time. So typically, we use 5 years for creep loss determination and shrinkage loss determination. And again, as I mentioned before, it depends on quite a few factors that are difficult to predict sometime. So this is the equation that relates the time-dependent creep coefficient, we call that C, based on the ultimate creep coefficient. So this is given us to us, unknown by us. And if I know the t in days, I can use this equation to convert Cu, which is the ultimate creep coefficient, to any time. For example, if I'm trying to calculate that at 90 days, I need to come in here, and you'll note this is a logarithmic scale. And you can go here and figure out what that value is. These are published in SCI. So from there on, we can figure out the creep loss. So here's the question again. Typical values of Cu that are given to us are between 2 and 4. So higher the strength of concrete, the higher the value. So I would say if you're using high strength concrete, high performance concrete, which is open to definition, then we tend to use the higher value. But if it's the lower strength concrete, we'll use the lower value of 2. So SCI ASC task committee is not in the SCI code, recommends 2.0 and 1.6 for pre-tension and post-tension structures. So after we figure out that what factor to use, then we figure out the creep loss, which is this value right here. Very simple equation. The actual time-dependent creep factor, FCS, is the stress in the concrete at tendon level. Again, you have to go back to those stress equations, and then you figure out what is the stress due to only sustained load at the tendon level. Then, as you know, these are well-known values. EC is the modulus of elasticity of concrete, which, as you know, SCI gives us equation to use there. And EPS is the modulus elasticity of steel, which is pretty constant across all different kinds of steel. Shrinkage loss. It has been shown that approximately 80% of shrinkage occurs in the first years. Shrinkage means that with time, it's a property of concrete. We cannot avoid it. It will shrink. Some concrete will shrink more. Some concrete will shrink less. It depends on water cement ratio and other factors, humidity and temperature, environmental conditions. Now, there's nothing wrong with shrinkage, but if you restrain that member, the concrete is not allowed to shrink. As a result, you may end up with shrinkage cracks. In USA, we see all the time, okay, in bridge decks, even new decks, they have these transverse cracks. So cracking is nothing wrong with that as long as we manage it. And as you know, that's why we provide shrinkage and temperature steel in slabs and decks. So that will cause loss. So how much loss? This is again is called the concrete shrinkage strain. It's sort of given to us. The values are here. These are the values. Typically varies between 500 to 1000 times 10 to the power minus 6. This is strain, so there's no unit attached to it. Again, that same task committee recommends 780 times 10 to the power minus 6, which you note will be about the midpoint between these two. So I would suggest that don't spend too much time on that. Just use the approximate value. And PCI stipulates a value of 820 times 10 to the power minus 6. Okay, so it's really up to the interpretation which value you want to use. Again, this graph for shrinkage variation looks very similar to the creep graph. So again, this is logarithmic scale to up to 5 years. This is the ratio of ultimate shrinkage versus actual shrinkage strain. There's a difference now because it has been shown that moist cured concrete shrinks more than steam cured. I mentioned the steam curing before. It may be difficult unless you have the setup to do this, especially in cast in place situations. But precasting, most yards in the USA are equipped with this because of the time savings and the labor saving and the cost saving. This is another benefit of steam curing. You can see that the shrinkage will be less, quite a bit less, which probably levels off with time. So these are the shrinkage strain ratios at time t. So this is the ultimate shrinkage strain. So what you do is you figure out what ultimate strain to use based on the previous slide. Then the T is in days. So this simple equation, okay, If you're using moist curing after 7 days, this is the equation to use. This gives you shrinkage, actual shrinkage strain, time dependent at the time. This is steam curing. If you're using steam curing, this is the equation to use. And then after you figure out that strain, it's a very simple matter of using Hooke's law by multiplying it by E of the steel to get the shrinkage loss. So there are ways out to the complicated formulas. There are simple equations that can be used. Okay, now friction loss is common for post-tensioning, not for pre-tensioning. Let me explain. What happens in friction loss is that you have this duct in post-tension members. Before you place the concrete, you stretch the steel and the steel is going to slide against the duct, right? You think it's in the middle point. It may not be in the middle point, especially for curved ducts. That can be an issue. So friction loss will happen because of the sliding effect. And that's taken care of by the friction loss. There are two kinds of friction loss: wobble friction due to unintentional misalignment. That means you didn't intend that to happen. And curvature friction due to intentional curvature if you have curved ducts. And this is from SCI code, section 1862. So these are the values given to us. It's an exponential function, looks complicated. There are values for this factor here, the exponent here, not greater than 0.3. ppx will be permitted computed by this. So these are long equations. Again, if you program that in a calculator or a spreadsheet, that's easily doable. And this is I think, in my judgment, this is the most complicated one to figure out. If it's pre-tensioning, you don't have to worry about it. This doesn't happen. So please don't find out friction loss in pre-tension members. But post-tensioning members, you have to figure it and factor into the total loss. The next one is called anchorage slip loss. So think about that. You are stretching these post-tensioning members and you are anchoring on one side and jacking from the other side. Then you are anchoring that on the other side as well. So the anchors are not perfect. Okay? There will be some loss, there will be some slippage within the anchorage. So what we do is we try to estimate that, and that will create loss in the member. So we do that, and then we factor that out in this loss. So manufacturers will give us that value. How much is that value? Okay. And in the example I did, I used a 3 millimeter slippage allowed. Even in pre-tensioning, that will happen because even within that casting anchorage, there will be some slippage. So here's the equation, very simple. If I can estimate that how much anchorage slip I'm allowing or happening, which I mentioned was about 3 millimeters, depending on the pre-stressing force. If I know the length of the strand and the E value for the steel, I can figure out the anchorage slip loss. Makes sense, right? So here are some tables I gathered for you. If you don't want to go through those trouble of finding the detailed losses, this is from Post-Tensioning Institute. PTI, Post-Tensioning Institute, is a very well-known organization in the US. They have published this in their post-tensioning manual. So depending on what kind of steel you have, do you have bar, do you have low relaxation strands, or do you have stress relief strands? If you have a slab, these are the values to use. If you have beams and joists, these are the values to use in megapascal. Now, these are approximate. As you see, it's a very broad. They're trying to just give you a broad spectrum of values. You need to use your judgment in using these values. But I have seen that depending on the circumstances, if you have usual cases of post-tensioning or pre-tensioning, if you have usual concrete, they are pretty reasonable. Okay. Now, one thing I like to point out here in the bottom is that they do not include friction loss. So if I use these values, I must add friction loss to this from the previous equations, and then I will get the desired values, the total lump sum loss. These are AASHTO lump sums. So these are for bridges. Sorry, let's go back here. So this is from AASHTO. It's kind of, again, approximate. So total loss depending on the concrete strength. So there are two strengths given. Nothing is given beyond that. I don't know if you can extrapolate that or not. So if I have pre-tensioning strand, this is the total loss, 310 megapascal. Post-tensioning wire strand, there's no value given here, by the way, for pre-tensioning for this concrete here. Post-tension, there are two values given, and for bars, these are the values given. Okay. Again, friction loss is not included. So AASHTO says you must figure out the friction loss and superimpose them onto these losses. So now we jump into flexural strength, very important, right? We do all the loss calculations, we do the stress checking, the member is fine, but how do we know the member is safe? So typically for beams, we check the flexural capacity and the shear capacity. Now you may have to do the torsion capacity. For compression members, the axial force capacity or beam column capacity and so on. So this is the equation from ACI. What we do is we use the same equation that we use in reinforced concrete, which is, as you know, which is AS Fy or Fs times D minus A over 2. So this is the reliability equation, which Dr. Ghosh, I'm sure, has covered in the previous lectures. So we just modify that. Instead of AS, we use APS. And instead of Fy, we use the actual stress in the tensile steel. So ACI gives us these equations in section 18.7.2. So if you have bond and tendons, we use this equation. It's kind of complicated, but I have the example which I've shown the application of this. And I won't spend too much time on this here. This is the omega equation. This is the omega prime, which is based on compression steel. If you don't have any, you can ignore that if you don't have any compression steel. And gamma P is based on the ratio of FPY over FPU. And if you have compression steel, which can be factored into that equation. So this is interesting. The depth of there are two depths you need to consider in pre-stress concrete design. One is the usual D, which is the effective depth to the non-pre-stress tension steel, and DP, which is the depth of the pre-stress steel. So they may be different. For example, if I have a stirrup, if I have additional reinforcement, this is the D to use. And if I'm going to the effective depth of the pre-stressing steel, I use DP. So there's a little bit of difference here between the reinforced concrete design and pre-stress concrete design. How to find those values? These are additional equations. Unbonded tendons, depending on the span to depth ratio, 18.4 equation. There's a limit on that. And more than 35 span to depth ratio, use this equation. So there's a lot to cover in this lecture. So I'm just giving you the overall ACI provisions, and please feel free to use them as you see fit. So the essence of the flexural design pre-stress concrete is that, as I mentioned before, you figure out the member proportion. That means the size, the shape, the width, and the depth based on the stress limits, right? Allowable stress method. So compression stress, I showed you the limits before. Tensile stress, I showed you the limits. And then you select the cross section, the pre-stress force and eccentricity, to make sure that you're within those limits. We cannot violate those limits. That's very important for that purpose. So one thing I like to point out, when you do allowable stress design, this is not LRFD. So please don't use load factors. No load factors, no fee factors in this calculation. This is service design. Just use the actual loads. Just similar to what we do when we find deflections for reinforced concrete members. We do not apply the load factors. We check the deflection only at full service load. That means we use P effective in that calculation. And partially pre-stressed beam means that the beam is not 100% in compression. So as I mentioned, showed that you in the previous slide, the bottom of the beam may be in somewhat in tension. For those, you need to control crack, which is very important. Again, if I impose those SCI tensile stress limits, I should be in good shape. Shear design is a different ball game. As you know, shear design is quite different. We are moving into SCI is moving into strut and tie design. SCI allows that. AASHTO allows strut and tie design for shear and torsion, or even for the whole beams. So this is all there, but I'm just going to fall back on the 08 edition. We didn't have strut and tie at that point. So main problem with the diagonal tension is that the diagonal cracking, right? As you know, the combination of shear and bending will give you diagonal tension. And because of the pre-stressing applied, the crack in your beam will be flatter, which is a good thing, right? Why is that a good thing? Because if I have a 45-degree crack angle for pure shear, and if I apply the normal stress from pre-stressing, it's going to be flatter. Flatter means that more stirrups will cross that diagonal crack line, and I have more shear capacity, right? So if I have inclined tendon, this is interesting. As you know, VC is the concrete shear capacity. V is the total shear. And this is the component from the tendon slope. So if I have a 10-degree slope, this will be reducing the shear. It's kind of small. If I assume VP to be 0, I'll be conservative. If you have a really steep profile, you can use that to your advantage in reducing the number of stirrups or increasing the spacing that you need. So I like to point out this cracking potential in pre-stressed concrete beams. Now this is a continuous beam. So continuous supports, this is important to understand the shear provisions. So at the bending moment, positive moment in the midspan, as you know, there will be midspan positive moment, typical for continuous beams. There will be crackings like this, patterns sort of this. Near the maximum moment to be kind of vertical, and then gradually become inclined, diagonal cracking as you go away from the maximum moment. This is called flexure shear cracking. Okay. Same thing happens here on the other side, negative moment, the cracking starts on the top and gradually progresses inward. Now, away from that, there'll be web shear. Okay. So web shear means that you're away from that. Here's a high shear region, maybe negative moment or no moment for simple support. Then the web shear will take over. So ACI gives us two equations, one for flexure shear cracking and one for web shear cracking. So in the SCI nomenclature, V sub D stands for self-weight shear. This is external shear. V sub P stands for pre-stressing shear, as I mentioned before. And VCI, total shear producing flexure shear failure. So here is the upper limit. Typically, I use this D sub P, which is the effective depth to the pre-stressing steel. If I don't know much, I just use 0.8H, which is the upper bound for this calculation. FD, flexure stress the bottom face from self-weight only. FCE is the compressive stress of the bottom face, axial and bending effects of the eccentric preset force included. So that's all inclusive at the bottom face. These are the equations straight from the ACI code. Critical section, as we know, is a d/2 from face of support. Critical, that's typical for shear design. As you know, ACI allows us to come out a distance d/2 and design for that shear at that point, which should be less than at the support section. Here is the VCI equation, flexure shear equation, shear capacity of concrete. I'm sure you know what the lambda factor is. Lambda factor is the effect of lightweight concrete on the strength of concrete. So ACI gives us the values if I use lightweight concrete. And then F prime C, usual BW is the width of the wave and so on. And then the moments are factored in here. It's a complicated equation. MCRE is the cracking moment, which is given by this equation. So if you do this by hand, it's going to take a long time. I'm just warning you that it will not be that simple to figure out, because I'm supposed to calculate from this equation the concrete shear capacity, from that equation, concrete shear capacity. Then I'm supposed to use the smaller one, which is the most conservative. Now here is a leeway out. Alternately, we are allowed to use this equation, which looks much simpler. For that, this is a variable over the span. You need to know the VU at every section, MU, ultimate load, ultimate shear, every section, and then you can figure this out. So either use these two or use these two. After that, it's a very simple matter to design the stirrup spacing, right? As you know, this is the equation, very well-known equation from ACI. Phi factor for shear, which is 0.75. AV, area of vertical steel or transverse steel. Fy, D, and Vu, the total shear force. Subtract this out. Now there is ACI equation for inclined stirrups, which I never seen being used. So I don't show it in my class lectures, or I'm not showing it here for you. Okay, so spacing limit for shear reinforcement. This is different again for pre-stressed concrete. So the spacing, maximum spacing should not exceed d/2. This is typical for non-pre-stressed, but for pre-stressed, it changes to 0.75 h, where the h is the total height of the pre-stressed member in millimeter, or 600 millimeter. It's very simple to understand and apply. Just want to show you the inside view of that I-beam I showed you before in the casting. Showed you the shear steel here. You can see them clearly, the stirrups jutting out of that I-beam. These are the steel forms I showed you before. And these dowels serve a big purpose. They give you the shear capacity because these are vertical stirrups. As you can imagine, that's the wave of the beam before casting. And they stick out. This is a bridge girder. We will transport to the site, and the deck will be cast on top. When it does, these will get embedded into the deck, and that will conveniently give us the composite action between the deck and the girder. That's very critical. If I use Astro provisions for bridges, we use 100% composite action, and that must be ensured. Although in practice, I've seen that no bridge is 100% composite. Okay, I showed you that diagram before. This is another view closer up. You can see the shear steel very closely spaced at the support. And we can increase that over there because the shear is maximum near the support of that beam. Even the ledge beams can have stirrups, and typically the ledge reinforcement will stick out from the main beam on the ledge, and that will provide any kind of shearing activity punching to this ledge that I showed you before. We're not done with shear reinforcement, okay? We need to look at minimum shear reinforcement. This is very similar to reinforced concrete, but their values are different. The equations look same. This is true when VU exceeds half of the shear strength, PBC, typical for reinforced concrete as well. So this is the AV minimum for pre-stressed concrete. Simple equation, but not less than this value here. So I'm just going to breeze through here because you can always fall back upon these numbers. I've shown the example where these are applied. This is ACI chapter 11, which deals with both shear and torsion. More minimum shear reinforcement provisions, shear reinforcement is required, and torsion is neglected. Okay, if torsion is not neglected, then this is the equation to use. So you need to do a judgment. Should I neglect torsion, or should I consider that? Then you have to use the proper equation. And all these terms should be well known by now, right? What they mean. So I talked about composite construction, and I firmly believe in that. If I have I-beam like this, it's useless because I must apply the load. And the live load is only applied through a composite deck or slab. Now, if I make it non-composite, that will not be too useful because the deck will be just a dead load or live load applied on the beam. The beam will still be asked to carry all the load. So composite construction makes sense. This is the hollow core slab I mentioned before, which is pretty common in the US. We hollow out the core by removing this concrete from the neutral axis. It has minimal effect on the strength of the slab. Then we can use a cast-in-place topping on that, top of that. This is single T with a cast-in-place topping. This is a double T, as I mentioned, with a cast-in-place topping. And there are many, many variations of this kind of composite construction. They are very useful for buildings and bridges. Showed that before. Showed actual construction, composite construction here. We have the beams pre-stressed. I see this is a bridge, this is a bend cap, and then we have the deck being cast on top of that. Okay? So by using the dowel bars from here, that will become composite. Another view of the composite construction. Now it can be steel too. This is a steel bridge. I can see the variable profile of the steel bridge, but the deck is composite. Steel is good, but there's no way to avoid concrete even in steel bridges because the deck will be made of concrete and somehow I have to make it composite. So there should be dowel bars on top of the steel girder. They'll be sticking out in the deck and that will make it composite. So I talked about the stages of loading before. So here is another view of a typical bridge that we use in the USA. This is precast eye girders, the dowel bars sticking out. You can see the deck, the cast-in-place deck. This is precast, that's cast-in-place. And we are using this innovative system. It's called precast panels. So this is pre-stressed, is precast, simple slabs. We place them on top of the eye girder. Then with the dowel sticking out, we cast the concrete. No need for formwork. Very useful for over traffic or over riverways or channels. There's no intervention at all, very fast construction. By allowing the precasting to take over, we can typically optimize the construction. This is very popular. Actually, in Texas, we're using a lot of the bridges, new bridges are like this. Typically, the precast panel is about 100 millimeter thick, and the cast-in-place on top is about another 100 millimeters. And they bond really well and serves the purpose. Okay, last thing in the lecture is the deflection. I'm trying to go a little bit quick here because I have two or three examples. I don't think I'll be able to cover all of them, but I'll try my best. So because precast concrete beams are more slender, of course they'll be slender because we're using precasting, right? That's the whole purpose, to economize the design. You will expect more deflection. Now, is deflection good or bad? That depends. Sometimes in a pre-stressed concrete beam, the camber will still remain at the end, which may have its own problem. If you have a bridge girder where the camber is unpredictable, you must adjust the slab, the deck thickness to adjust to that. Okay, we call that humping. That's unpredictable, so we really can't really predict camber very well. It also depends on environmental conditions. So, but we still try. Okay, if I have excessive camber, it can be dangerous on a bridge. The pavement will be uneven, can cause accidents, and tied to excessive deflection is excessive vibration. I have seen many new bridges. Where I was looking at a bridge in Dallas last week, where it has unusual vibration. The span was 150 feet long, so that is a telltale sign that the bridge is not serviceable because more vibration means more cracking. And also you don't want to have a bridge where the people are traveling over it and they feel that high vibration. They may feel unsafe. If it's a building, then excessive roof camber may create drainage issues. You don't want the water to pool on top of the roof from rain or whatever. because that can cause additional durability issues. Okay, and then it can cause additional cracking as well. So as I mentioned, the shrinkage, creep, and relaxation reduce camber with time. So SEI does not give us any deflection tables, period. So we have to fall back upon something else. I borrowed this from PCI manual, and I like this table. They are really very, very user-friendly. So I took only the parts from the pre-stressed concrete part. You can see the pre-stressed pattern here. This is kind of strange. I don't know how that can be possible, but this is common, not common. This is common. Now this is only a single hold down linear profile of the pre-stressing. This is kind of 3 linear profile. This is like a variable parabolic profile. So they really give us these nice tables. This is a camber table here. Okay, if I know the moment, I can figure out easily the camber. Very convenient. There's another table later on. So I always use these tables in my practice. I give it to the students, and it not only gives you the deflection, the PCI tables give you maximum moments, maximum shears. I've never seen any comprehensive design aid like that. So these are very valuable. You can use them in your design if you want. So after you figure this out, these are the camber, then you have to superimpose the other values, right? Those would be the dead load deflection, the live load deflection, which are not reflected here, but you can find them in other table, and you need to find the net deflection. So I just want to mention here that the strand designation is in metric. Here they are given. Okay, these are pre-stressing strands. They go from number 6 to number 18 and depend on the grade also. Actually, this is the SI unit, and that's the equivalent US unit. So these are also very useful tables. I have used them in my examples. Okay, so I know there are a lot of questions coming up. I have about, I would say, 35 minutes in my lecture time. Well, maybe up to 20 minutes because I need to answer the questions. So I need to leave by 10:45 to attend my class at 11. But anyway, maybe I'll go through this example here, and then if I can just browse to the other two. This is kind of shorter, so let's tackle this one first. What I've done, I've taken I-beam, symmetric I-beam, a section, the area of concrete is given, and the area of pre-stressing is also given. So suppose they're known, and all the dimensions are given. And the other information given is the F prime C, modulus of concrete, the creep coefficient, beta 1 value for the stress block, as you know, and the grade of the steel, and the 7-wire strand that are used, effective pre-stress. So I'm assuming the loss is taking over here. Moment of inertia of the section, which you can figure out yourself, concrete area, section modulus, and radius of gyration. So you can estimate them, you can figure them out. These are all based on gross area of the concrete. Pre-stressing is placed here, AP. So I know that from the center out of the section, 132 millimeter would be the eccentricity, right? From here to there. So what I have done here, tackling a section like that with variable depth is difficult. So I have taken an approximation. For example, I have converted this trapezoid into a rectangle. So that should provide almost same answers, and same thing here. So just following back on what I showed you from the SEI code, first ratio I need to check is this value here. Okay, the FPY, yield strength of steel, and the FPU, both are given. So SEI says I must be more than that, so I'm fine, 0.86. Based on that, I can use one of the equations given in the SEI. So steel ratio, well, that's well known now, right? The rho value, as you know, is the area of the pre-stressing steel divided by BD. So this is same as reinforced concrete or pre-stressed concrete. So I solved it. I found a rho value of 0.0048, which is the steel ratio. Then I went into the SCI equation for FPS, which is the useful stress in the steel, pre-stressing steel. So all the values are here. Gamma P 0.4 from that equation. Rho P I calculated, FPU is given, beta 1 of 0.85, and then F prime C of 27.6 megapascal plus omega, which is given also in the SCI. I end up with 1472.8 megapascal, which is, this is the section of SCI that you need to pay attention to, the SCI 08 code. Then I figured out the omega, which is called the pre-stress reinforcement index, which is very simple, rho FY over F prime C. Fy is given, F prime C is given, so we get 0.26. I hope it's clear so far. So based on that, the beam is classified as a tension control. That's very important, right? Because you don't want to have ductile beam. SCI does not allow over-reinforced beams, as you know, or compression control beams. This is the check. This is not the same check that is done for the reinforced concrete beam, which is a different value, as you know. So be careful to use this provision for checking tension control. Tension control means the beam is ductile, that is allowed, and that will have sufficient give so we can take evasive actions or we can repair the beam before it's too late. Then, just the usual, we figure out the depth of the stress block A. So the depth of the stress block, positive moment will be here. Question is it rectangular beam or T-beam? That we figure out here. So this is a P Fy over 0.85 F prime CB. Okay. So I'm using the whole flange thickness to start with to check whether it is T-beam or rectangular beam. I found out that the depth of the stress block A for the Whitney stress block is 133 millimeter. Okay, so because that exceeded the flange thickness, okay, my average flange thickness is 127 millimeter. Now at this point, 133 is almost same as 127, but it's still a little bit away. Okay, so I can't really cut corners. So I still apply the T-beam philosophy, although I could be very close applying the rectangular philosophy, but I didn't want to take any chances. So as you know, in the T-beam, we divide this into two sections. We take the overhanging part of the flange, which is this part here. Then we take the web part. We take them separately. We find Mn1 and Mn2. Then we superimpose them to get the combined capacity. So that's what I did here. This is the part, which is the web part. We call that APW, same FPS, and that's the part due to overhanging. Now this logic is taught in all undergraduate classes, so I'm sure you're aware of that. That's the overhanging part. That's the force from the overhanging part. And subtracting it out from the web part, or the overall part, this is the overall capacity, AP, FPS. So this is AP times FPS. Subtracting out the flange part, we get the web part, which is 345 kilonewton. Then we recalculate the stress block in the web, which is based on this one. So this is, AP, FP over 0.85 F prime CB. Now we're using BW because we're in the web now. The web width is 102 millimeter. Moving along here, that's the moment strength. Now we have Phi-Mn1. This is not Phi-Mn. Phi is not applied here. This is nominal flexural strength. Phi should be applied here. If it's tension controlled, Phi should be 0.9. And then this is the moment from the first part. This is the moment from the second part. Note how I use the 127 here for the flange width and the different one here for the web width. And the total capacity is 352 kilonewton meter. So that's the flexural strength, ultimate flexural strength. And what we do is we reduce it by Phi factor, as you know. Then we can compare that with M sub u, which is the ultimate moment in the span. Then we can figure out if Pmn is more than mu, the section is safe. If Pmn is less than mu, it's unsafe. If Pmn is exactly equal to mu, you don't want that because you want there will be a little bit of reserve strength in there. So try to stay away from when they're exactly equal, because there can be so many uncertainties in load or the strength or the other issues which are inherent in concrete. I think that's the end of this example. The second one is shear design. Okay, so this is one a little bit more involved. So I have an unequal I-beam here. Okay, unequal I means top flange is different than the bottom flange. Here is the pre-stressing. And let me try to move this a little bit here. So sections is given, okay, overall depth. Then the depth of the centroid, they are unequal because top flange is heavier than the bottom flange. So here we have something interesting. We have a linear profile for the strands. So anchoring here goes down to here. Then it flattens out in the midspan. Okay. And we are supposed to figure out the shear design at 3 meters from the support. Okay. Overall, the beam center line is 6.8 meters. This is half of the span. And AP is given to us at 1129 millimeters square. And then some, this is not really conforming to the centroid. This is draped all the way up. So this will cause additional positive moment at the support. Loads are given to us. Superimposed dead load of 5 kilonewton per meter, service live load of 18 kilonewton, and so on. F prime C of 35 megapascal. And FPU of the tendons is 1860 megapascal. Effective pre-stress. So we need to figure out the vertical stirrups at a point 3 meters from the support. You can do this anywhere. You can do this at the critical section, d over 2 from the face of the support. This is like arbitrary section I selected to show the application. Of course, we have to find the shear here and then design accordingly. So we figured this out, the gross moment of inertia, the area of concrete, and the radius of gyration squared. So knowing the dP through the center part of the span and eccentricity of 290 millimeter, so we figured out the eccentricity, which is very simple. If you go back here, if you know this profile, how far is going up from here, this simple triangle, and by taking that angle, you can figure out how much is that eccentricity. I cannot use that one because I'm calculating shear capacity here. So it's a very simple matter of triangle from trigonometry, which I did here. So I found the dP now at that point at 3 meters from the support. And the ACI code says that I can assume the depth in shear calculation to be 0.8 of the overall height, 0.88. Remember the equation I showed you before from the ACI code? So that's reflected here. I took that, and that value is 589 millimeter. Then I went into the two equations, the flexure shear crack equation and the web shear crack equation, and calculated them separately. So I'll probably rush through here because I'll take about 5 more minutes here. So found FPE, which is at the level of the pre-stress, the stress here. Make sure to use effective pre-stress because we are designing for the service condition, not for the initial condition. Then I figured out the moments and shears. This is old information. You can use whatever way you want. You can use a spreadsheet, or you can use code values. These are equations for the moments at that point. So I found the dead load moment, found the shear value at that point, then found out FD, which is the stress at the bottom of the beam for the probe moment for the self-weight moment. which is MC over I. Then found out M cracking. Okay, probably just show you the equations here. Then shear and moment at section 3 meters from the support. Okay, we figured that out from there. Okay, applying the live load and the superimposed load. So I found VCI based on that. So that's the flexure shear capacity of concrete. This is only concrete. No steel is involved in this. And then I went to the web shear crack equation, which is VCW. Again, use PE, found the centroidal stress, and I tried to show the vertical component of the pre-stress. Remember, I told you that that would be reducing your stress if you want to do that. Then I found out VCW. So here's important, something important here. VCW is 389 and VCI is 145. Of course, this one controls, right? The lower one controls. So that I assume that to be my governing concrete strength, VC. Then found out the VU at that point at 3 meters from the support. Very simple statics equation. Then figured out VVC. As you know, that's the criteria which controls the stirrup spacing. Subtracting out VVC from VU. I just use number 10 stirrups as a first approximation. This is the area of the 2 leg stirrup. Now, if I use a double T beam, of course, it may be 4 times. So you have to be careful, sum up the area of the stirrup with the proper number of legs considered. Then I use the stirrup spacing equation. I use a few factor of 0.75, not 0.9, because I'm designing for shear according to ACI, and everything else is given. I found a spacing of 414.7 millimeter from the strength equation. Then I went down and checked the minimum web steel, as I mentioned before. This one equation, second equation in terms of S, the unknown spacing. So this is where you spend most of the time doing all the detailed check from ACI, but there's no way around it. Sometimes that takes more time than doing the actual design of the steel. So based on here, if I solve this based on the minimum one, I get a spacing of 887 based on the minimum web steel criteria. And then additional criteria is that I must use smaller of 600 millimeter or 0.75 H, which is this. So comparing this one with this one and that one, of course, we see that this one controls. So my strength control, this one did not control. So I used a spacing of 414 millimeter for the spacing. And number 10 worked out fine. If that doesn't work out, then you have to go back and change the stirrup size to be within the allowable limits. So Bodhi, if it's okay, I'd like to stop now because I have another example on pre-stress loss, which I don't have time to go through now. It's kind of detailed. I request you to look at that example, and you spare time if you have any, and then reach out to me if you have any questions. Okay. What I did at the end was I summarized all the loss calculations that I calculated from the actual equations. Then I found out the percentage of the loss based on the capacity of the strands. Then I compared with the lump sum. Sorry.
Then is it possible to cover this thing in the next webinar or something like that?
Yeah, I know we are short of time, so I could stop right here, Bodhi. Thank you, and let's take some questions for the next 15 minutes or so. So should I do a question and answer?
Yeah. So you have to go to the top of the screen.
Yeah.
And Q&A.
Okay.
Yeah. So you should see the question and answers on your screen.
So I see there are 31 questions.
Yeah, if you're not able to see something, or like if you're facing some problem, then I can read the questions for you. So
Let's see. Let me see how I can toggle through. I have to toggle through here, right? I don't see the whole. Can I see the whole list at one time?
yeah, you can also pop out. There's a small pop out button at the corner.
Can you see this my screen?
No.
Oh, you cannot see my screen. Okay.
Yeah. I mean, that
Too
won't
weird.
be visible. Yeah, if it is too difficult, I can read out the questions.
Okay, let me. I think I can go through one by one here. Hold on.
Okay.
Okay. The first question is there is a mistake in the handout before the.
Yeah, that is different. You
Oh,
go from the below because the initial questions, they were related to quiz and other things. I have handled those things. So
oh, sorry.
those are answered already. So
Okay, let me scroll through here. Hard to see here. Let's see. Is there a more efficient way of doing this? Let me see here. Okay. If he's from Bangladesh, I think he means me. Okay. Can you please request him to conduct the class in Bangla? Okay. So that's a good question, but we had discussion in the team and we decided to stay in English. I'll be glad to do this in Bengali. I'm a Bengali myself, but the the decision was to keep it in English just in case audiences who are not from Bangladesh can also use the webinars. So that's a good question, but that's the decision was made team-wise. I asked him during his trial if he's comfortable teaching in Bangla.
that is my answer. So Dr. Yazdani, let me read out the questions because you don't have much time.
Okay.
Okay. So I will read out the first question. So one is, can we use pre-stressed slab or beams in a high seismic area for building construction?
I don't see why not. You know, you have to have the seismic resilience. So you can always use that for whatever purpose you want. You have to apply the lateral loads. That's not only seismic, it's all wind as well. You can have rigid connections, you know, between the different components, which is possible as I showed you with the dowel actions and so forth. I don't see why not. You know, even in USA, when we build bridges in high seismic states like California or Portland, we are using multiple span continuous bridge structures. So it's entirely possible. The next one, Bodhi.
Do you have any tolerance value for providing intentional alignment of tendons as per PTI or ASTHO?
Can you repeat the first part?
Do you have any tolerance value for providing intentional alignment of tendons as per PTI and or ASTHO?
Yeah, I think I don't have that value on top of my head. I'm sure it's published in PTI. I can send it to you if you can contact me or to the team. So that's important because, as I mentioned before, the unintentional alignment, if there is a problem, then it will cause additional friction loss, right? So that value should be known, and there's a tolerance that is satisfied, has to be satisfied in the field or in the precast yard. The next one.
Can we pre-camber the post tensionings?
You're breaking up. Can you speak up again, Bodhi?
Yeah. Like I'm just trying to rephrase the question. Just a second.
Yeah.
Can a simply supported PSC girder, post-tension girder, be pre-cambered?
Okay, so simply supported post-tension girder. Let me think. I don't think that's necessary to even post-tension simply supported girder. I don't know why you would do that. To be speaking honestly, you can easily use if you have the precast facility, you can use that. But if you don't have that, then it has to be cast in place. So yeah, it can be done. I don't see why not. I'm not sure what the question asking for. Budhi, can you repeat the question again?
Can a simply supported PSC girder, post-tension concrete girder, be pre-cambered?
Oh, pre-cambered. Okay, I see the question now. Okay, so if you design for the camber wisely, if you apply the deflection, you can pre-camber it it'll be difficult with the formwork. You can easily imagine you have to kind of vary the formwork to give it the pre-camber. Honestly speaking, I don't know why that would be necessary, because you can always design your camber. If you want more camber, you can always design the section or design the pre-stressing and estimate the losses, so you can try to estimate the camber. Now, camber is very difficult, as I mentioned. It's very difficult to predict camber. You can design all day, but at the end of the day, we can always end up with a different camber in the bridges, for example. That's why I mentioned that. That's why constructability is very important. You have to properly adjust for any kind of unintended camber. It can be too high sometimes. So you have to build that in your structure and adjust the slab or the deck profile to conform to that. Next question.
Is it possible to pre-stress a column member, and how will be the connection foundation in such a case?
So that's a good question. We are using pre-stress piles all the time. Okay, so you can optimize the section. By pre-stressing that, you can optimize it. Connection detailing is important for constructability. You have to have proper connection between the pile or the pier cap or the pier and to the foundation. You have to extend the steel, adjusting for the development lengths, proper development lengths, and also, as you know, sometimes that can control the design. I design a beam with a certain profile of pre-stressing and certain profile of the stirrups. Then I design a column, and then I design the foundation. So they have to come together in constructability, and sometimes they don't mesh each other. So sometimes you have to go back and alter your design so that you have to adjust your spacings and stuff like that. And that can control, I have seen many cases that controls the design. Next one, Bodhi.
Yeah, in the seismic design category D, second, I will just rephrase the questions.
Okay.
Can we use precast structures in seismic design category D, as joints are critical? Yeah, this question is not very clear to me.
Yeah, I think I can only guess what the intent of the question is. So I think he or she is trying to say that can we use precast members in high seismic areas? It depends. If you are using just I-beams, simple support beams in seismic areas, that may not fly because in Texas we are using all the time those kind of members, simply supported members, because Texas has a low seismic category in AASHTO. But as I mentioned before, precasting is not only simply supported beams. Now it can be continuous beams, like I showed you the segmental bridge construction. So using those kind of systems, you can usually achieve seismic resiliency that you desire in bridges. Next question.
Yeah, so you were talking about pre-stressed concrete, right? So there's similar question for pre-stressed concrete. That can pre-stressed concrete be designed as part of seismic force resisting system, or is there any limitation to use of pre-stressed concrete as special moment frames or intermediate moment frames, etc.?
No, I think there is no limit on using pre-stressed concrete for seismic zones. You just have to be creative, use the proper shape and proper span and proper connections so that you can transmit. Actually, if you go to AASHTO, I'll be covering that in the future webinars. There, you are supposed to design for any kind of lateral load. You're supposed to design for wind, you're supposed to design for seismic or flood or whatever. Or even we're thinking about for fire in the future and blast in the future. So we're looking at all different scenarios. So how do you accomplish that? You must transfer the force from the superstructure into the substructure. All that has to be built into there, into the structure, and that can be done. We need to anticipate that and then design or construct accordingly.
Yeah, Dr. Ghosh is also there with us. Dr. Ghosh, if you want to add something, you can jump in because you are already a co-host.
I'm a co-host, okay. Yeah, it's difficult to, the bridge world I'm not familiar with, but in buildings, we have very definite restrictions on, pre-stressed and precast are kind of different things. For precast construction, we can do both frames and wall construction in high seismic areas, but we have to follow very specific provisions that are given in ACI 318. And in view of these questions, when I talk about seismic design over the next couple of weeks, I will make specific reference to them. Pre-stressed members used not to be allowed as part of the seismic force resisting system. Now they are, but there are restrictions on how much, basically the in a beam, at least 75% of the moment has to be resisted by mild reinforcement. The pre-stressing cannot be responsible for more than 25%. So there is pretty severe restrictions on the conditions under which you can use pre-stressed members as part of the seismic force resisting system in high seismic design categories. So buildings I will cover in more detail, and Dr. Saidi will be talking about seismic design of bridges in March. And I think he will provide answers to some of the questions on what may be the restrictions in high seismic areas on bridge members.
Thank you, Dr. Ghosh. So another question is, if we want to check the capacity of a 20-year-old pre-stressed concrete girder, what is the procedure to determine material strength?
Good question. Okay. I'm doing structural evaluation all the time, and that you're right. That's where much of the work is. We have many more bridges and buildings that are old and deteriorating versus new construction. So in terms of finding the in situ strength of concrete, especially when the as-built plans are missing, we use few tricks. We use non-destructive evaluation, for example, hammer sounding. That is pretty efficient if you can calibrate it right. You have to have the right equipment. Then we take cores, in situ cores, 4x8, 400 millimeter by 200 millimeter typically. Then we be careful not to cut through any rebars. Then we take it to the lab and then do cylinder strength. From there, we can get a pretty good idea about the strength of the concrete at that time. Okay, next one.
Yeah. How to control buckling of PSC girder in case the tendons are not in the geometric center?
Well, that's a good question. We can look at the profile of the girder and try to predict the buckling behavior. You can use diaphragms, for example, if you are not sure about the eccentricity of the tendons. And that can in bridges in US, diaphragms are being gradually removed or not being considered because diaphragms create their own problems with kind of lateral buckling. But so that's why it's so important to predict what the situation, control that in construction very wisely so that you don't exceed the tolerances that are given by the codes. Next one.
Yeah. Second, I'm just checking the questions in room 2.
Okay.
So in a composite structure like flyover, how much maximum cantilever can we provide? Cantilever.
Let me think. So in a flyover, when you say cantilever, I don't know what you mean. There should not be cantilever longitudinally speaking. Cantilever could be overhang of the girders. Is that, I think that's what he's mentioning, the overhang on the transversely. Because as in buildings we have cantilevered slabs and balconies, but in bridges we don't have longitudinal cantilevering. You understand? So there are provisions in AASHTO that provides you the design of the overhangs. We use what we call lever rule for that. And then we design accordingly based on the potential of limit state in the overhangs. And there are no specific value given. You have to calculate that based on the AASHTO equations for limit state in the overhanging part of that. Typically, even in precast construction, your overhang will be cast in place. And you have to make sure that it blends well with the existing structure.
Okay.
Next one.
Okay, Dr. Yazdani. So it is already 10:45, and as you said, right, that you have to jump into another class.
Are there many other questions left?
There are a couple of questions.
Yeah, I can go maybe a couple of more minutes. Yeah, go ahead.
Okay.
I mean, what I was suggesting is that, is it possible to download the questions, send to me? Maybe
Yeah,
I can respond somehow.
So I save the questions for each and every webinar.
Okay.
Usually. So I can send you the questions too. So if you want to come up with answers afterwards.
Okay.
But you have already answered most of the questions. I don't see any more questions. But there is one question that has been asked 2-3 times. So I will just.
Okay. Sure.
So for the post-tension and pre-tension system, is there any advantage of pre-tension over post-tension or vice versa? Under what conditions should we go for post-tension over pre-tension and vice versa?
Yeah, that's a good question. So there are advantage and disadvantage to both. Pre-tensioning, as I mentioned, is done typically in the yard. So you can control the quality better. So if you're worried, you have kind of concerns about the construction process, and environmental conditions, quality of concrete, if possible, you can pre-tension it. That way you can avoid some of the construction issues and get better quality concrete. Now, for that, you must have some kind of yard available. You cannot do pre-tensioning on the bridge itself or the building itself. So that should be available, the facilities, the anchorage, and things like that, either on site or in a precast yard. Now, post-tensioning, as I mentioned, is typically done in the field. So if you have long spans, if you have multiple span, continuous spans, precasting will not be very efficient. So in that case, use post-tensioning in cast-in-place situations if you wish to do that. Provided, of course, you'll be facing some of the construction issues that I mentioned. So it's really a choice that you have to make. Simple structures, precast girders, simple construction, you can do that. But then multiple choices, multiple continuous spans. For example, I showed you that segmental construction. That is precast and also cast in place. So sometimes it's hybrid. It's not all cast in place, or is not all or it's not all precast as well. Okay. Well, enjoyed it thoroughly. Thank you so much for your time and attention.